My name is Colin Bakum. I'm currently finishing up at CCP for engineering, and I'm interning at the Singh Center for Nanotechnology. So far, my experience in the Singh Center has been very eye-opening. Just the amount of technologies that we're using here, the advanced tools that we get to use, and all the manufacturing techniques have really taught me a lot about how we're currently manufacturing at a small scale. In particular, my focus is on small semiconductors, and so I've been learning a lot about how those are actually made in the real world. So my current project is working on graphene transistors. These are types of transistors that rather than using doped silicon, we're using small graphene layers, which are thin carbon layers, and they have some interesting electrical properties that may make them very useful for us in the future. So there are several features of graphene that make them very useful to us in a transistor setting. So graphene, at its most basic level, is a lattice of carbon atoms that are arranged in hexagons that are tiled together. It is strictly one atom thick in its purest form, although sometimes they do end up a little thicker when we build them practically. It's very flexible and stronger than other materials at that equivalent thickness. One of the things that we really care about is its high carrier mobility, which means how fast can charge travel through the surface. And what's really interesting is that this carrier mobility remains very high at room temperature, much higher than traditional semiconductor materials. When we bring this over to the graphene transistor, we can see that carrier mobility makes for very high switching speeds. Switching speeds are one of the main physical barriers in all sorts of transistor applications. It just basically means how long does it react to a change in the direction of charge. And so because of that high carrier mobility, we get a very high frequency for switching. A graphene transistor has no band gap. This means that current can never be completely blocked, and that it has an actual lowest current possible at something we like to call the Dirac point. One of the advantages of this non-existent band gap is for something that we call continuous small signal amplification. This lack of a band gap means that there's no noise floor to our input signal, and functionally what this results in is a very high sensitivity. This makes it very good for sensory applications. And one of the great things about that high switching speed is that it allows it for use in very fast RF applications. One of the big ones is changing magnetic fields from radio signals, and it allows for a lot of clarity to those signals, particularly when we have to amplify them. I think this internship is for anyone who's studying the sciences, anyone who's interested in manufacturing or creating tools that could be useful. It may be hard to see at first, but the very small, the nanotechnology, can be found in almost any field. So I think anyone who's interested in tools or building can find a place here.